Welcome back to The Explainer. Today, we're tearing down the massive, globally expanding wind energy sector. But we aren't just looking at the basics of how wind turns into electricity. Instead, we're going to reveal the hidden sustainability metrics that truly define this industry's success, its profitability, and frankly, its future viability.
Okay, let's dive right in. When we talk about wind technology and project developers, we aren't just talking about a single product rolling off an assembly line. These are massive entities that manufacture the turbines, the highly engineered blades, and the towering support structures. But it's important to remember their business model doesn't just stop at the factory door. They actually develop these wind energy projects from the ground up. They manage the construction, and crucially, they offer the long-term post-sale maintenance and support services that keep those turbines spinning for decades.
Now, to really grasp how these developers operate, we're going to look at this complex industry through the rigorous lens of the SASB and SASB sustainability standards. Basically, this framework provides us with a highly reliable, standardized look at the industry's true risks. It cuts right through the greenwashing and gives us the hard, quantifiable metrics that investors and developers actually use to measure operational resilience and environmental impact.
So here's the life cycle journey we'll be taking today. We'll cover 1. The blueprint. 2. Sourcing materials. 3. Designing efficiency. 4. Ecological impacts. And finally, 5. Safety and operations.
All right, let's kick things off with Phase 1, the blueprint. The complete life cycle of a wind project developer goes way beyond just selling a giant piece of machinery. The business model spans from raw material manufacturing to the highly complex construction and siting of the turbines, straight through to project management, and finally to those inherently hazardous post-sale operations and maintenance. To truly understand the risks in this industry, we absolutely have to look at every single step of this chain.
Which brings us to Phase 2, sourcing materials. Right at the very beginning of the supply chain, these turbines require some highly specific, frankly hard-to-pronounce critical minerals. We're talking about rare earth elements like neodymium, dysprosium, and yttrium, alongside crucial metals like tantalum, tungsten, and platinum group metals. These are absolutely essential, especially for modern, highly reliable direct-drive turbines. Those are quickly becoming the industry standard, but the catch is they require significantly more of these materials than your traditional drivetrains.
But if we zoom out for a second, relying on these specific rare earth elements exposes developers to immense risks. For starters, there's a very low substitution ratio, meaning you can't just easily swap these out for something else if your supply dries up. Add to that the fact that these deposits are heavily concentrated in just a few countries, and you suddenly introduce massive geopolitical risks, heavy competition from other tech industries, and incredibly volatile pricing constraints that can instantly threaten a developer's bottom line.
Let's move into Phase 3. Designing efficiency.
To keep a handle on these incredibly costly inputs, the industry tracks very specific materials efficiency metrics. To ensure they aren't eating away all the profits, developers track the top 5 materials consumed by weight. We're talking heavy hitters like steel and fiberglass to optimize energy outputs against these massive material costs. Getting even more granular, companies calculate a key efficiency metric known as the average top head mass. It's actually a pretty clever formula. They take the mass of the top head, which includes the turbine nacelle and the rotor, but entirely excludes the blades, and divide it by the turbine's megawatt capacity. This gives developers a precise look at exactly how many metric tons of material are required to generate a single megawatt of power. It constantly pushes engineers to innovate lighter, more powerful designs.
Next up is Phase 4, ecological impacts.
There's a real irony in this industry, right? Building green energy farms comes with some severe ecological and community challenges. Developers face completely unique hurdles depending on where they build. Onshore installations frequently clash with local communities over noise emissions, extensive land use, and visual aesthetics. Meanwhile, offshore developments present an entirely different set of headaches, including severe marine ecosystem disruption and potential radar interference. Whether it's on land or at sea, environmental risks and community opposition can completely stall or literally kill a multi-million-dollar project. The gritty reality of project development is quantified through strict SASB metrics. First up, the A-weighted sound power level, which is essentially exactly how loud these turbines are, has to be meticulously measured. Second, and perhaps most tellingly, is the financial metric of backlog cancellations. This tracks the actual currency amount of turbine orders that are canceled or deferred directly because of community pushback or ecological permitting failures. It proves, without a doubt, that community relations directly impact the balance sheet.
So how do they combat these cancellations? Well, the industry is fighting back with some fascinating physical technologies and software.
They're incorporating blade heating elements, plus wildlife deterrents like radar detection and ultrasonic transmitters to protect local animal populations. They also utilize advanced SCADA software systems capable of something called sudden curtailment. This means they can rapidly shut down or adjust the spinning of the blades the second a flock of birds or a bat colony is detected, perfectly blending hardware and software to mitigate ecological harm.
Finally, let's look at Phase 5, Safety in Operations.
When calculating the total recordable incident rate, or TIIR, the wind industry relies on one absolutely crucial baseline number, 200,000. So what does this actually mean? Well, it represents the total number of hours that 100 full-time workers, working 40 hours a week for 50 weeks a year, provide annually. It standardizes exactly how companies report workplace injuries, allowing investors to compare safety records apples to apples across the globe.
And why is tracking this safety metric so vital? Because operations and maintenance work in the wind sector is inherently dangerous. Technicians are dealing with extreme heights, massive moving mechanical parts, and serious high-voltage electrical dangers. Tracking injuries, medical treatments, and fatalities isn't just about regulatory compliance. It directly affects a wind farm's insurance costs and the developer's overall reputation. A poor safety record can literally lock a developer out of securing future tender requests entirely.
Which really leaves us with this final thought. As the global demand for renewable energy surges, and as these turbines grow taller and wildly more complex to meet that demand, can this industry actually balance rapid, profitable expansion with the strict demands of ecological preservation and human safety? Understanding the metrics we've explored today is really the only way to find out. Thank you so much for joining me for this explainer, and keep learning.